All right, so here we are again. We're ready to carry on with our review. If you remember, we have one chapter that is dedicated to reviewing what you've learned in the past that will be important for Calc 1. So they are calling these chapters P1, P2, P3, and P4, P for preliminary. So let's get back to where we left off last time, which is we were looking at the concept of symmetry. Okay. And so what is that all about? Well, there's three different ways we can find symmetry uh, for a function. Okay. So for example, we might have this case, a nice parabola, y equals x squared. So I normally used to writing on the whiteboard, and so I'm still getting used to the idea of writing on a tablet. So for a while, my graphs will be a little awkward looking, I think, but I think I'm getting there. I'm improving a little bit here. But anyway, y equals x squared. Now the idea of symmetry with respect to the vertical axis or y-axis is that everything on the left of this axis is a mirror image of everything that's on the right. So it's symmetry with respect to the vertical axis, which of course is just another name for the y-axis. And it's nice to look at a graph and see if it's symmetrical or not, but there's a much more formal way of doing this. What we'd like to be able to do is show that for any point, let's say here, we'll call this xy, there must also exist the point on the other side of the axis, which would be negative xy. Okay. So in other words, and it doesn't matter which x and y we choose, they both have to exist in the same function for every case, in order for this to be symmetrical with respect to the vertical axis. So how could you show that algebraically? Well, if you write this instead of y equals x squared, if you write it instead as f of x is x squared, we can show that f of negative x, which simply means that all x's are replaced with negative x, is the same thing. Okay, so it literally doesn't matter which x we choose. This could be any x in the domain of this function, and the same thing will be true. So in other words, f of x, f of negative x, um, and not just for a few cases, for every case, for all x in the domain of f of x. And that's all you need to prove that this function is symmetrical with respect to the vertical axis. Okay. Um, So now what about symmetry with respect to the horizontal axis? That would be something like this, where for every, let's say, point xy, you must also have the point um, x negative y. Okay. And although now the interesting part about this one is that this one is actually not a function. It does not qualify as a function because if you remember, I mentioned last time that in order to be a function, if you remember, it must be the case each x is uniquely associated with a single value of y. Okay, so in other words, what we have here is a case where that's not true because for x, we have two different y's, y and negative y. So if you remember from way, way back in pre-calculus, um, if we have, let's say, a set of ordered pairs, something like this, Well, in this case, these ordered pairs represent a relation, okay, but not a function. Because here you see x is 2 and y is 3, but with this ordered pair, x is 2 and y is 4, and that rules it out right there. So it's a relation, but it's not a function. But if instead we had something like this, well, it's a relation. It's also a relation, but it is a function. So in other words, it's a relation and a function. Any set of ordered pairs is automatically a relation, but we have to test to see if it's also a function. And again, the whole idea here is that um, each x is associated with one y and no more, exactly one. So sometimes you see these ordered pairs drawn in a slightly different way, which I think might be a little easier to visualize. Let's say here's your x and here's your y. Okay, this is meant to represent a set of numbers that belong to these two. This on the left, you're seeing all the x's that we can substitute. And so if you go back to this first case, you have 1, 2, 2 and 3, and 3 and 4. You may remember seeing a graph like this in your travels. Okay, here we go. So if you look again at this set of ordered pairs, 1, 2, 2, 3, which you already know is not a function. It might be a little easier to see why with this type of graph. So what do we have? 1, 2, let me just double check. 2, 3, 2, 4, and 3, 5. So here's the problem. So this x is associated with 2. This x is associated with 3. But here it is. It's also associated with 4. And then 3 is associated with 5. And so here is the holdup. This is what means that it's not a function, because x equals 2 is associated with both 3 and 4, and therefore it is not a function. On the other hand, this set of ordered pairs is a function, and we can show it more easily, I think, with this type of graph. Let's do the same thing. We'll draw this graph. And of course, this time things work a little differently because each of these x's is associated with exactly one y. So therefore, this is a function. In fact, you could write f of x here. And furthermore, you can define the set on the left as the domain of this function, and this is the range. Okay. All right. So that's how that works. So this graph is not a function. You can see why, because you've got x going with x, y, and x equals negative y. So it is not a function. And I think last time I mentioned that you can tell by looking at a graph if it's a function or not with the so-called vertical line test. Shows if a graph represents a function. And so basically, let me just show you two possible cases. So the one on the left, if you drew any vertical line that you choose, if you notice, it does not touch the graph more than once. Okay, but over here it does. Okay, so I don't know off the top of my head what the equation would be here, but it is not a function. And you can tell just by looking at the fact that the vertical line crosses it twice. Okay. Okay, so there's different ways we can test whether or not a set of ordered pairs is a function or not. Okay. Now, the third type of symmetry, besides symmetry from left to right or top to bottom, meaning um, this one is symmetry with respect to the vertical axis or left to right. This is symmetry with respect to the horizontal axis, which of course is just a fancy name for the x-axis, to the horizontal axis. But then there's another possibility which involves the origin. So a function like this, well, this one, if you notice, although of course this diagram is not exactly perfect, but what I'm trying to show here is that if you could imagine, here's our first quadrant and here's our third quadrant. The two of them are identical, or they're, think of them as mirror images of each other. And so for any point x, y up here, we must have the corresponding point down here, minus x minus y. Okay, that's symmetry with respect to the origin. Now, this can actually work in this, two different ways. You could also have this case, and again, even though we're now looking at the second and the fourth quadrant, this also counts as symmetry with respect to the origin. So, in other words, for this point, for example, would be negative x but positive y. And down here, you would have the equivalent positive x but negative y. And so that's how you would know that you have symmetry with respect to the origin, either this case or this case. Okay. So now they also go on to explain to us it's sometimes, if you look carefully at the functions, if you look at the exponents, it should be in many cases possible to determine whether there is symmetry or not. Okay. Without having to formally test it algebraically. You can certainly do that. And you probably should, but just sometimes the graph isn't, or the function itself is enough. So the examples they give us are these. Hold on, here it is. All right. So here they're giving us a general rule. If we have a polynomial, which could be of any degree, in this case, it happens to be of degree 4, if all the exponents are even numbers, then we will have symmetry with respect to the vertical axis. Okay. Actually, I think they're going to, if they don't, you know what we could do? We could go to Symbol Lab and show it. Um, Let me do that real fast. Hold on. All right. So y equals, whoops, x to the fourth. Nope, sorry, it was 2x to the fourth minus x squared plus 2. And even though it's maybe not exactly what you're expecting, if you notice, the graph is identical on both sides of this vertical axis. So we call that symmetry with respect to the vertical axis. Okay. So again, what it really means is that for every xy over here, there's got to be a corresponding negative x y on this side. Now then they have now here, what they've done is they've changed the exponents to positive, or sorry, odd numbers. Here we have x cubed. The negative x has an implied exponent of 1, which is, of course, an odd number. So what they want us to do is see if this one has symmetry with respect to the vertical axis or the origin. Now, because it's an odd, as I just showed you, y equals x cubed is symmetrical with respect to the origin. So chances are this one will be 2. Okay, so let's take a look. 2x cubed minus x. And look, oh, and again, it's not crazy obvious. I mean, it looks pretty clear that the first and the third quadrants are mirror images of each other, but you can prove it. Um, well, actually, wait a minute. No, hold on a second. What we'd like to do here is prove this algebraically. I mean, it's hard to tell. Like I said, it's hard to tell just by looking. Um, I mean, you really have to be good at geometry to look at this and say, I'm certain that there's symmetry with respect to the origin, that the first and the third quadrants are identical to each other. I mean, I suppose it's clear that they are, but I mean, what if it's not that obvious? And it's such a bizarre shape that it's hard to be sure. Here's how you would prove it. Um, so what they want you to do is this. Yeah, it's kind of strange looking, but yes, you can see that they are correct. But 2x cubed minus x, let's take a look at this. So remember, now we can see from the graph that it might be symmetrical with respect to the um, origin, meaning that the first and third quadrants are identical to each other. So which that means is that for every xy in the original function, there must also be the corresponding pair negative x, negative y. Okay. So how do we prove that? That's really our target for every f of negative x. There, we have it's identical to negative f of x. So f of negative x looks like this. So remember, again, what you're trying to do here is every x is now being replaced with negative x. Okay, that's good. What about the original function? Negative f of x would therefore be negative. The original function, remember, was 2x cubed minus x. Oh, yeah, there they are. They are identical to each other. In other words, we just proved that f of negative x was negative f of positive x. And therefore, that implies symmetry with respect to the origin. All right, so I think that's all we need to say about symmetry at the moment. Remember, this is just meant to review. We haven't started the new material just yet. Points of intersection, of course, sometimes we need to find where two functions intersect each other. In this particular case, they're showing us that we have a parabola and a straight line, and we'd like to know where they cross. And in this particular case, you can clearly see that they cross twice. And so how would you find those points? Well, the parabola, they're giving us the equation x squared minus y equals 3. Now, I don't know why they had to do that. I would prefer to see it written like this. Or very just simply y equals x squared minus 3. I think if it's written in this form, it's easier to visualize what it looks like. It's basically going to look something like this. And the intercept will be this negative 3. The straight line, x, and they did it again, x minus y equals 1. And of course, we know that that looks something like this. Has a slope of 1, and the vertical intercept is 0, negative 1. So where do they cross? This is what we're looking for. Well, we know that at those 2 points, they're equal to each other. So what we're going to do is this. We're going to set these equal to each other and solve for x and y. So we set these two equal to each other. So we can write it like this: x squared minus 3 equals x minus 1. Now we're going to get everything onto the left-hand side. And we see that we have a quadratic equation here. Now, you can do one of two things here. You can factor it, or you can use our old friend, the quadratic formula. Now, just in case it's been a while, why don't we practice with the quadratic formula? So for a quadratic equation that's written in the standard form, the solutions, meaning the points where the parabola crosses the horizontal axis, can be found with our old friend, minus b plus and minus b squared minus 4ac all over 2a. This is the quadratic formula. Oh, you didn't forget that. No, of course you didn't. Nobody forgets this formula. That's been my experience. So keep in mind, though, that these a's, b's, and c's are coefficients. A is 1. That's the coefficient of x squared. B is negative 1. That's the coefficient of x, negative x. And then c is negative 2. Okay, so what does that give us? Okay. So what do we have? 1 plus or minus 1. 1 - 1 squared is obviously 1 plus 8. Okay. So of course the square root of 9 is 3. And then this plus and minus symbol means we're doing two things. We're both subtracting and adding 3 from 1, and then we divide by 2. All right, so the two x's are -1 and 2. Okay. Now we can find the corresponding y's from either of the two equations because we know that they're equal with the two functions cross. So let's do the simpler one, which is y equals x minus 1. All right, so 1 point is -1, -2. And I think they showed that on the graph here. Yeah, there it is, -1, -2. And then when x equals 2, so the other point that we need is 2 comma 1. Okay, and so that's the other point of intersection between the two. There you go. Okay. Now, here they're briefly introducing some mathematical models. I think we can skip over this and jump ahead into the next section. Um, Part 2 of the preliminary notes is all about linear models and rates of change. Okay, now, of course, they're reviewing here the slope of a line. I don't know if you've forgotten how that works. I doubt it. But they just want to remind you that what the slope actually represents is the rate of change of y with respect to x. I don't know if that went where I wanted it to. No, it did not. Hold on. There we go. All right. So, I mean, this is a very complicated looking graph, but all they're trying to show you is that we have 2 points, x1, y1, x2, y2. If I want to know the slope between those 2 points, delta y is simply the difference between y2 and y1, and delta x is the difference between x2 and x1, and then the ratio of those two is the slope. Okay? That's all there is to it. Okay. Now, there are some interesting cases they would like you to remember. The line here that has the points, endpoints, -2, 0, and 3, 1, has a slope of 1/5, which means it's positively sloped. You can think of that as moving in a northeasterly direction. And if you notice, the slope is very small, so that it's a relatively flat line. If the slope is 0, we'll end up with a horizontal line, and you can see that that's because no matter what happens to x, y is always equal to 2. In fact, that actually is the illustration of the line y equals 2. And of course, based on the standard form for a linear function, this indicates that m is 0. That's how you can tell. But when you think about it, I mean, since M is defined as delta Y over delta X, the important detail here is that no matter what delta X is, delta Y will always be zero, and therefore the slope is zero. Now, contrast this with, let's say, something like this. It's easy to get this one confused. The other extreme case that you might run into is a vertical line. Well, that one's very confusing. So in this case, the slope, and if you notice, it's the now the x that's never changing. Ooh, we have division by zero. You know, there's one thing you're never allowed to do in math, it's divide by zero. So therefore, the slope is said to be undefined. And in fact, based on what we said earlier, this is not even a function in the first place because x equals 3 is associated with an infinite number of y's. And then the last case we need to consider is the negative slope. And that means we're moving, think of it as a southeasterly direction. Okay. So the slope can be positive or negative, or zero or undefined. All right. Let's see. Now, everybody's used to this form for writing a linear equation. This is known as the slope-intercept form. Because it tells us explicitly the intercept and the slope. There's two other possibilities, though, which you don't see anywhere near as often, but you could also express the equation of a straight line in the following way. Where you're only seeing, instead of the slope and the intercept, you're seeing a single point and the slope. And so this is called the point slope form. Okay. Now, sometimes they'll ask you to do this. They'll ask you for the equation in the point slope form, and they mean do it this way. So if you write it out in the traditional slope intercept form, at least the WebAssign will mark you wrong. They won't accept it because they're asking you for a specific format. Um, so they're going to ask us to solve for this one. They're going to say, well, listen, what if you have a slope of 3 and the point 1, -2 is on the line? They're going to have us start with the point slope form. So you can think of this as x1 and y1. And they want us to convert it into the traditional format, the slope-intercept form. Okay. So all we're going to do is a little algebra. All right. So in other words, here's what we're going to do. So why don't we, let's add 3 to both sides. No, sorry, let's not do that. Let's subtract 2 from both sides. And that's it. We're done. And that's now suddenly in the form that we're more comfortable with. And you can see it has a positive slope and a negative intercept. Rates of change, it's basically the same idea. Um, let's take a quick look at this example. Let's say the population of Texas was 25.2 million in 2010. All right. Now, when they give you time like this, time is considered to be the X variable, the independent variable. So we have a population 25.2 in 2010, and it went up to 29.4 in the year 2020. Now, what they want you to do is not only figure out the average change per year, but make a forecast for the year 2028, assuming that nothing changes. So the change of the population per year is delta y over delta x. 29.4 minus 25.2 over, and of course, this is a 10-year interval. So we have a change of 4.2 over 10. And of course, it's understood these are in millions. So then what they're saying is, well, if that's the case, where will we be in 8 years? Okay, well, that's the linear function that they're saying, listen, you got this function, and we have those 2 points. Where would we be in 2028? So one way to do this is to say, well, we're currently at 29.4. And then in 8 years, if we increase by 0.42 per year, we're going to have, let's see what that is. 32.76. And that's, of course, assuming that nothing changes, that the slope doesn't change, the rate of change is the same throughout that entire period. But if it is, that's our prediction, 32.76, or they rounded it up to 38. Let's see, what else do they want us to do? I think this is where they're giving us a little practice drawing these. Oh, and by the way, I did mention that there's other ways of expressing this, but the two you're most likely to run into are slope intercept and point slope. Here's a blast from the past. Parallel and perpendicular lines. So how does that work? And so I noticed that, people tend not to forget how parallel lines work, but they might forget how perpendicular lines work. So we said that two lines are parallel if they have the same slope. Okay, so let's say we have Y equals 3x plus 4, y equals 3x minus 2. If we were to plot these, you'd see, okay, that's not too terrible. Y equals 3x plus 4 and 3x minus 2. So you can see they'll never cross. Okay, they're parallel to each other. Now, perpendicular is a little different. Perpendicular lines, if you remember, they meet at right angles. How can you tell if they're perpendicular? Okay, the product of their slopes is -1. Okay, so in other words, if you had something like that, what would end up happening? And even though the drawing again isn't perfect, you can see that more or less they are right angles where they cross, and that's what we're aiming for. So you can see by multiplying out 3 by -1, -1/3 rather, equals -1, and therefore they're perpendicular. Now, most lines are not perpendicular or parallel. So, in fact, we know one thing about straight lines is that they always cross, as long as they have a different slope, they always cross at exactly one point. What separates perpendicular lines from the others is the way they cross. Okay, we know that that's going to give us a right angle where they cross. So you should be able to figure out without any difficulty whether two lines are parallel, perpendicular, or possibly neither. I'm sure they're going to ask about this in WebAssign. What else do they want us to do? Okay, well, that was section 2. What's coming up in section 3? P3, that is. Okay, so now they're going to get back to, oh, so there's that notation I was using with you earlier. Um, they're going to give us more complicated functions. We're going to reintroduce to us the concept of domain and range. Um, remind us how to learn how to, graph these functions, carry out the vertical line test, some basic transformations of functions, polynomials, something we haven't thought about in a while, rational functions, composite functions, zeros of functions, odd and even functions. There's a lot going on here. So I think it's time for us to stop right here. And in our next section, we'll go through this section 3 and possibly we'll start 4. But hopefully all this material is coming back to you and you're realizing that you haven't really forgotten any of it and that you're still comfortable with it, which is good because we'll need it throughout the rest of this course. Okay, so I'll see you next time.